You are listening to Kubernetes Bytes, a podcast bringing you the latest from the world of cloud-native data management. My name is Ryan Wallner, and I'm joined by Bhavin Shah, coming to you from Boston, Massachusetts. We'll be sharing our thoughts on recent cloud-native news and talking to industry experts about their experiences and challenges managing the wealth of data in today's cloud-native ecosystem.
Good morning, good afternoon, and good evening, wherever you are. We are coming to you from Boston, Massachusetts. Today is May 30th, 2024. Hope everyone is doing well and staying safe. Let's dive into it. This is going to be a Bhavin only episode. I guess we do have an awesome guest to talk about model training and model checkpointing on top of Kubernetes. But for the intro and the key takeaways section, I guess you guys are stuck with me. So now that we have kind of introduced the topic for the episode itself, let's dive into some cloud native news. First up, I have a CVE that was found late last week, like right around the Memorial Day weekend here in the US. If you are using versions 2.0.7 through 3.0.3 of FluentBit, make sure you upgrade your FluentBit versions to 3.0.4, because in those versions that I just specified, there is a new critical severity vulnerability called linguistic lumberjack, CVE 2024-4323, if that number makes any sense to you. But it affects those FluentBit versions, and which involves a memory corruption error, potentially leading to denial of service attacks or denial of service, information disclosure, or even remote code execution. So this has been identified. We link a blog from Aqua Security, a vendor in the Kubernetes security ecosystem, on how this CVE can be actually exploited on top of your Kubernetes clusters, and then what are the best practices. I think if you are looking for just one easy answer, I think it's upgrading to FluentBit version 3.0.4 from all the previous versions that we just listed. So keep an eye out for that in your environments and make sure you fix those. Next up, we have some awesome news from the Kubernetes community. One thing that that caught my eye was the CNCF, or the Kubernetes community, worked on removing more than 1 million lines of code from Kubernetes. More than 1 million, guys. It's 1.5 million lines of code. They removed all the cloud provider integrations that were in tree. And they have successfully migrated them outside from the core Kubernetes repository to an external plugin based architecture. So remember how we went through the same transition for the storage plugins that were built into Kubernetes and then eventually driven outside with the CSI plugin framework. Kubernetes ecosystem is going through a similar transition for all the different cloud providers like Amazon and Google and Microsoft. And so the Kubernetes repository itself, 1.5 million lines of code, I think this also reduced the size of the deployment or the binary by 40%. So huge efficiency gains from the community. So kudos to everybody who worked on this. But I just wanted to highlight that as part of today's episode. Then we had the Microsoft Build conference last week, and Microsoft announced an interesting solution for AKS, something called AKS Automatic. It is currently in preview. It's not generally available in all the regions, but AKS Automatic is kind of that even easier to use tier for your inside AKS, right? So if you're deploying an AKS cluster today, you're responsible for configuring the cluster, how many nodes you need, what kind of CNI, how do you handle security, how do you scale or size your cluster so it can support all the different applications that you want to deploy on top, how do you plan for upgrades of different versions. With AKS Automatic, all of these things go away. All you need to do during an AKS Automatic cluster deployment is give it a name, select a region, specify a resource group, and maybe a couple more details, and then that's it. Microsoft or the AKS team will worry about or will take over the configuration, scaling, security, and even upgrades for your Kubernetes resources. So let's say your organization hasn't adopted Kubernetes for all their applications, right? But we have seen a gradual increase in the number of ecosystem vendors that are providing their applications as a containerized application. So if you want to use some off-the-shelf application and run it inside your inside your environment or inside your cloud environment, you need a Kubernetes cluster. Instead of becoming Kubernetes expert, this gives you, I guess, an easy way to just point the cluster to the repository or the source code for that application that you're trying to deploy, and then Microsoft handles the amount of nodes that you need in the cluster, and also making sure that it's secure and it's running the latest and greatest versions. I'm not sure about the greatest version, but it's running a supported version of Kubernetes for sure. We'll have links in the show notes for you to check out the announcement around AKS Automatic. And then finally, today, as part of the news segment, we have another acquisition. So I know last time we covered the new debt financing round that Harness had announced. I think they're just following it up with an acquisition. Harness is now acquiring Split Software. So Split Software allows teams to release software updates quickly and safely through advanced feature flagging, A/B testing, and real-time experimentation. You can, if you are a LaunchDarkly user, you can think about them as kind of a LaunchDarkly competitor, but now part of Harness. Split, the acquisition price was not shared publicly, but looking at the crunch base and how much money Split had actually raised, they did raise over $100 million, or right up to $100 million before this acquisition was announced. So somewhere in that range, I would assume. So we'll have the link in the show notes to read more about the acquisition on Harness's site. So if you are a Split customer, congrats, now you are a Harness customer. But again, congratulations to everybody at Split Software. Acquisitions are always cool, or exits are always cool. Gives a way for early employees to have some form of liquidity event, right? Because many organizations are not ready to start going public and try their hands at an IPO or a public offering, either in the US or somewhere else. But yeah, that's it for the news segment today. As I hinted earlier, today's episode is going to be another AI themed episode, but we are going deeper into one specific topic. We are focusing on model training, and even inside model training, we are focusing on model checkpoints and how a startup like Memverge can help you optimize your GPU resource utilization, help you reduce your cloud costs, things like that. So I'm personally excited for this discussion. Let's invite Bernie and talk to him about this topic.
This episode is brought to you by our friends from NetHopper, a Boston-based company founded to help enterprises achieve their cloud infrastructure and application modernization goals. NetHopper is ideal for enterprises looking to accelerate their platform engineering efforts and reduce time to market, reduce cognitive load on developers, and leverage junior engineers to manage and support cloud-mandated upgrades for a growing number of Kubernetes clusters and application dependencies. NetHopper enables enterprises to jumpstart platform engineering with KAOPS, a cloud-native, GitOps-centric platform framework to help them build their internal developer platforms or IDPs. KAOPS is completely agnostic to the Kubernetes distribution or cloud infrastructure being used and supports everything including EKS, GKE, Rancher, OpenShift, etc. NetHopper KAOPS is also available on the AWS Marketplace. Learn more about KAOPS and get a free demo by sending them an email to info@nethopper.io or download their free version using mynethopper.com/auth.
Hey, Bernie, welcome to the Kubernetes Bytes podcast. I'm really glad to have you on the show to educate us on AI on Kubernetes specifically, right? So I know I gave away the topic a bit, but why don't you introduce yourself and tell our listeners what you do?
Sure. Thanks, Bhavin, for inviting me. I really appreciate it. So yes, my name is Bernie Wu. I'm the VP of Strategic Partnerships and Business Development for a company called Memverge. And Memverge is a Bay Area tech startup, and is focused on solving some of the biggest memory problems facing the computer industry and users, particularly when it comes to AI ML workloads. And just some of my background prior to Memverge, I've been working in both startups and established companies, both in hardware and software, and pretty much been in what I would call the infrastructure area. So I've been doing everything from semiconductors, started my career at Intel, then flash storage, object storage, software-defined, virtualized storage, data protection, cybersecurity, database engines, worked on cloud and infrastructure as a service. So I like to call myself a plumber. I do a lot of this infrastructure.
A lot of buzzwords for sure, but that sounds like a fun career that you have had so far. And then with the AI wave, I'm so glad to see that you're continuing to be on the bleeding edge, right?
Yeah.
Okay, so the reason we are doing this podcast is because I was listening to the data on Kubernetes presentations from Paris a couple of months back. I wasn't able to attend in person, so I was just playing catch up. And you had a really great talk. So I want to start with like one basic question, right? You were at Data on Kubernetes Day. So is AI more of a Kubernetes stateful workload or a stateless workload? And the reason I asked that is initially, right, when back in November of 2020, when OpenAI first released GPT 3.5, everybody is like, okay, if you want to run these models locally, you run it and then you interact with it as a chatbot. You don't really have to manage any state along with it. So in May of 2024, is AI still stateless or is it becoming more stateful?
Yeah, it's definitely becoming more and more stateful, and most AI today is actually running on Kubernetes. So just to back up a little bit on Kubernetes itself, it's kind of an interesting shift that Kubernetes has to go through itself. So the original objective of Kubernetes back in 2014 was to be a cloud native platform and for running web services. And at the same time, I thought it was interesting because it was not only a new platform, it was a new programming model. So the whole concept of a containerized microservice was developed, and it absolutely had to be stateless. The Kubernetes purists would be all over you if you didn't write a totally stateless microservice architecture. And and so it was actually, for that use case, was ideal. I mean, it allowed it to become a highly scalable, highly elastic, independently scalable microservices. So, and then anything that had to do with state, you tucked in a database that was off the Kubernetes cluster, basically. And since then, what I've seen happen with Kubernetes is that it grew in popularity and it became more of a vendor agnostic, neutral, open source hybrid cloud operating system. And so now everybody wanted to start moving all their kinds of workloads, including stateful workloads. So that started happening in 2017, I think. And now, as we fast forward to this AI large language model area in particular, you find that the model training stage is a very data intensive, stateful batch operation. And that's at a high level, that's a kind of a mismatch for the original approach of Kubernetes. So basically, you have this giant data digester ingesting a huge amount of data, computing all these model weights, and then back propagating them, and then so rinse, wash, repeat. It's an iteration until it gets close enough to some level of model accuracy, and so that can take quite a while to execute that kind of program. It's definitely not a microservice architecture. And what I found was interesting is that the groundbreaking model ChatGPT OpenAI was developed on Kubernetes using several thousand Kubernetes nodes. So that's the training side. It's definitely a highly stateful kind of operation. Now, what's interesting is on the inferencing side, once the models have been trained, initially, as you mentioned, the initial ChatGPT was essentially stateless. It would, as soon as you asked it a question, it would forget what it was.
There was no long-running context windows.
Yeah, and then also it didn't remember anything after December 2021 or whatever it was to stop training. So it would answer if you asked any question after that, like who won the last NBA championship, it would give you a ridiculous answer because it didn't know. Yeah. So that wasn't very useful. I mean, it was enough to cause a tipping point in the industry, but to make it really useful, it really needs to be more and more stateful. And most importantly, it needs to avoid hallucination, the phenomenon of hallucination in AI models. So that means that these AI models, especially in the inferencing stage, need to be grounded in a database or some source of truth even current real-time information to make sure that they're not generating fictitious results. And so people are starting to use these vectorized databases, and they're starting to do domain-specific fine-tuning and all this kind of stuff. And not only that, the context window is getting larger and larger. You used to be able to ask it a 20 word question. Now you can 500 word. You can throw a whole book at it now, and it'll answer it.
Yeah. I think at Google I/O they announced that you can give Gemini Pro like a 1,500-page PDF document in just one question, as the context window is now so big, and you can ask it questions.
So that's essentially state. That's memory state that has to be kept, and because there could be a dialogue over several hours or days over that area. So basically, inferencing is becoming more and more stateful, and people are creating even pipelines. So it used to be just a one-shot inferencing. Ask the question, here's the answer. Now a lot of times it's a pipeline, and it's decomposed into multiple queries, and there's even an agent running around now to guide the whole response to the user. So definitely going that way, yeah.
Okay, that's awesome, right? I think especially for our audience, which is more concerned or more focused on like the storage aspects around Kubernetes, is definitely like glad to hear the answer. Like, okay, AI on Kubernetes is a stateful thing. Eventually, you will end up using all the proprietary data you have inside your organization, either to train your own models, fine-tune your models, or even if you're running inference kinds of workloads, you'll build something like a RAG architecture to use the data and use that business intelligence that you have built to better serve your customers. But I want to go back and focus more on like model training. You used OpenAI as an example, right? Like, okay, they used a huge Kubernetes cluster to train their, and they still do, like they use that as the infrastructure to train their GPT models. But how are these companies training their models, right? Is it happening only in the cloud, or a mix of hybrid, like on-prem and the cloud? What kind of tools are they using? Can you shed some light on that?
Yeah, sure. So I think a lot of people initially started playing around with OpenAI. It was easiest, very, very convenient. You could just be anybody, just download a notebook and do a little bit of hacking on OpenAI. People are doing a lot of that kind of work. And then I think what's happening is that people now that it's past the kind of the toy stage, novelty stage, people want to look at putting these into real enterprise workloads. And a lot of enterprises have a huge amount of proprietary data. And they also, at the same time, people have also discovered that, hey, we don't need such a gigantic model. We can use smaller models that are fine-tuned and connected to RAG or whatever, and make them more domain-specific.
Yeah.
So what I'm seeing is that actually a lot of companies are developing dozens or even hundreds of models that are fine-tuned, domain-specific. Maybe one's in charge of a call center, and one's in charge of looking at the latest information on a particular stock ticker, and consolidating that into a nice summary. Another model is working on being a co-pilot for converting Java, COBOL into Java. These are examples that I've come across in the financial service area. So there's a sub-movement to doing some of this stuff on-prem or in using smaller open models like Llama or whatever. And the tool chain initially a few years ago it was dominated by TensorFlow, but more and more of it now is based on PyTorch. People are pretty much standardizing on PyTorch, and there's a whole bunch of frameworks out there. So it's actually people like Ray and NVIDIA, PyTorch Lightning, DeepSpeed. There's a whole bunch of training frameworks that are being built. And some of them also are using tools to extract all these experiments. So we're still heavily in this experimentation phase. People are using notebooks to, at the individual data science level, they're keeping notebooks that kind of sit at the top of this stack of software. And then farther down in the plumbing, what you see are projects like Kubeflow for Kubernetes, which has a nice set of tools for doing model serving and fine tuning and the workflow itself on various operators. So it's starting to gel now. The whole pipeline, and I think Kubernetes is really going to be the platform of choice along with these different stacks. Yeah.
Gotcha. And you said a key word there, right? I want to focus on that, like pipeline, or if you also, I think another word that we can use for a pipeline is like an directed acyclical graph,
Right.
basically a pipeline of sorts or a graph of sorts that you are building to train your model. Can you talk about like what are the different phases involved? I know this is our way of getting to the core of the topic, which is using or how do we take model checkpoints, but can you first walk us through like the higher level stages, and then we can deep dive into the actual training phase?
Yeah. So initially, obviously, people are ingesting data. They're doing some sort of processing or filtering of this data, to remove the bias or things like that. And then it goes into a training phase. That's another major stage of the pipeline. After it gets out of that, there's a lot of optimization, fine tuning, because then so there's this baseline model, whether they develop it, train it themselves, or they use existing models from Hugging Face or whatever. They'll then go into a fine tuning phase, and then eventually it moves into a production phase or inferencing phase, and needs to be connected to databases for using RAG and things like that. So there's a lot of phases, and there's constantly going to be iteration between all those phases, of the pipeline. So yeah, it's a pretty complicated workflow, and the requirements on the infrastructure, vary tremendously. Some parts of inferencing are very memory intensive, other areas are GPU intensive, and so it's really a whole new ball game right now.
For sure. So I think now I want to talk more around what checkpoints are and why do we need them? Like, for example, right? Like when Meta announced their Llama 3, the 7B and the 8 billion and 70 billion parameters models, they said they had to cut this because they had to start training the next one. So these are like really long running training jobs, like can span hours to days to weeks to even months, right? That these jobs are running.
Yeah.
How do we make sure that if anything fails at the infrastructure layer, it doesn't, I don't lose all the work that I did, and how do model checkpoints play a role there?
Yeah. So there's a lot of these training frameworks like PyTorch and TensorFlow actually have built-in checkpointing capabilities, and actually I believe certain versions of Kubeflow also have some level of checkpointing for what I call the pipeline seams, between the stages. So the whole idea, one of the key use cases. And I think there's at least 3 different use cases for that kind of what I call model framework checkpointing. One very important use case is to be able to keep versions of the model. So you're doing this iteration process to train the model, and at some point you decide, well, the model is good enough, but that's difficult to know a priori. So a lot of times you have to test this model, and then you find out with other data outside of the training batch and find out how well it works or doesn't work. And sometimes you find that, for example, you may have overtrained the model. So you actually want to roll back to a previous epoch where it's less trained, because if it's overtrained, then you can't handle any variations as well in queries. So checkpointing is used sometimes to roll back the model to a earlier training epoch and use that as the final version of the model.
Gotcha.
So another use for these checkpoints is for hyperparameter tuning. So not only you want to get the right kind of model, but you also want it to be the most efficient. So there's tuning knobs on batch sizes and other high level parameters that affect the performance of the model. And so you don't want to go all the way back and retrain every time you twiddle a hyperparameter to see what the effect is. So that's another use case. And the third use case is actually has to do with the fact that, a lot of these training models take a long time to run, and you have a crash, hardware fails, something like that, and you don't want to start, from 2 weeks ago. Maybe 2 hours ago is acceptable, but 2 weeks ago, no way. So
those GPU resources are very expensive. You don't want to lose 2 weeks of worth of work.
Right. So a lot of it is to just roll back for recovery purposes. Yeah.
So, Bernie, the way you were describing a model checkpoint, right? It sounded awfully close to like what a storage level snapshot is. But obviously, that's not all, right? Can you expand on like all the different layers that are involved when a model checkpoint has to be taken to save the work, basically?
Yeah. So a model checkpoint is actually not as sophisticated as, since you and I came from the storage snapshot business. It's not as sophisticated as a storage snapshot. It basically, a model checkpoint is simply just stop the whole thing and copy everything from memory to files. It's just a bucket brigade, and then annotate it so you know what version it is, and everything has got to be obviously time done in synchronization. So that's the essence of model checkpointing technology today. So if you do a lot of checkpointing, there can be a significant amount of overhead as you're trying to drain all this memory onto to some file system for safekeeping. So that is sort of a problem with the current type of checkpointing that's going on. And
who's doing these?
Sorry, go ahead.
Yeah, and who's doing or taking these like checkpoints, right? Like, is this the developers or data scientists? You said these are done through PyTorch or TensorFlow, or some of those tools, right?
So the persona for these checkpoints is really the data scientists. They're trying to preserve their work. They're trying to fine tune or tune the hyperparameters. They're trying to make sure their job gets done. So they want to have checkpoints so they don't have to start all over again. So right now those are all done at the coding level for the data scientists.
Gotcha.
Check your checkpoints. Sometimes you do every other epoch because there's too much overhead or whatever. So there's a bunch of things like that. Yeah.
And data scientists usually don't care about the infrastructure. So if the operations team or the IT teams inside these organizations, right, if they wanted to have some sort of control, do they have to use tools like PyTorch? Like, how do they make sure that they are meeting their own SLAs and taking these checkpoints and not just relying on the data scientists to hopefully do their job and use these checkpointing technologies?
Yeah, that's where our type of checkpointing comes into play. What we have developed, and it's not fully out there yet, but there are some early adopters out there for what we call transparent checkpointing. So the idea is that we're doing a checkpointing that's more at the platform, ML, ops, engineering level. And the reason we call it transparent is because it involves no intervention by data scientists, no code changes, nothing. And the idea is that whatever is being checkpointed or snapshotted at that level, one has to be really high speed, because if it really took a long time, the data scientists kind of get mad because it takes too long, and why is this thing all of a sudden seizing up and all that kind of stuff. So performance is really important when you're doing it at that level. And then also, transparency, and the fact that nothing is, the data scientist doesn't have to change any scripts or code or anything like that. And then, and so that type of checkpointing is really a tool that's aimed at the ML ops and platform engineering guys. And the idea is to be able to, one of the main use cases is to improve resilience of the overall architecture. Because GPUs are like light bulbs; they burn out. And wouldn't it be nice if when you detect the error rate of a GPU creeping up, that you magically checkpoint it and move it somewhere else, and the people using the GPU cluster above you don't even notice, right? So those are the kinds of things that can be done with it. Another big thing is that as time goes on, there's going to be less emphasis on training, more emphasis on inferencing. And training, if you think about it, when you train a model, you just kind of train it once for a use case and then you got to cover. But what happens with inferencing is that it scales in proportion to the number of users, right? So as the number of users go up, the amount of inferencing goes up, and costs can skyrocket if you don't do what you can to optimize it. So a lot of people are concerned about how much power GPUs use and what the utilization rate is. So checkpointing at the AI ML layer or platform layer can be used as part of a scheduler to improve the what we call bin packing of the different AI workloads and get higher utilization of GPUs. So if you look back at actually these large models, like OpenAI's models or whatever, a lot of them reported only 35% GPU utilization.
Yeah.
So if you can imagine, if you could drive that utilization through having, better job scheduling and all that, and they were just dedicated to training things. So they were just trying to train something for the sake of training and beating the other guy. But later on, when we get to inferencing, having 35% idle GPUs is pretty costly. So
the only people that will be happy are NVIDIA shareholders and NVIDIA employees. Yeah, exactly. That's it. Like nobody else will be happy with that.
Exactly. Yeah. So that's where this checkpointing can be used to help in architecture similar to auto scaling on Kubernetes to drive up the utilization per node.
Gotcha. And Bernie, right? Like I haven't trained a model myself, but I wanted to see ask you how long do these checkpoints actually take? Like you said, you have to basically dump everything that's in memory onto a file at the storage layer, right? And looking back, I think these GPUs, they have gigabytes and gigabytes of memory. And so how long does a checkpoint actually take?
So a checkpoint, there's physics involved in it. It takes so much time to move memory. And one of the things that we have done is in developing our checkpointing technology in the industry is we started out with the open source. There's an open source checkpointing project out there called CREO, which stands for Checkpoint, Restore, and User Space. So it's designed to checkpoint things in user space on the Linux platform. And we've enhanced that. We built our own enhancements around it because right now, the time to do a checkpoint can be excessive. The time to copy all that memory and all that kind of stuff. So we've enhanced it by in two ways. If you're from the storage industry, you remember you had full snapshots, and then also had incremental snapshots. And incrementals are a lot faster because you're only doing the deltas between the last full snapshot or the last incremental. And then offline, you can stack them incrementals and make a full kind of snapshot. So we've implemented that kind of capability to keep the snapshot overhead down.
Nice. Some change block tracking.
Yeah, exactly. Incremental memory snapshots, right? Since most of the stuff that we're trying to checkpoint is in memory, you have to keep as much of the workload in memory as possible. Otherwise, the execution of these GPUs gets really, really bad. And then the second thing is we're doing things asynchronously. So normally what would happen is that these checkpoints would go straight from memory into file. So there's a whole serialization process and it's going to be bled out to the file. And so you're bound by the speed of the network and bound by the speed of the file system, blah, 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 blah. So what we're doing is we're actually doing that kind of memory snapshot. And then we immediately, once we start the snapshot, just like from the storage industry, we immediately release the application. So it can go back into production mode and then asynchronously copy the memory snapshot, which could be thin because it's only a delta to the file system. So we use an asynchronous approach as opposed to a synchronous approach to speed up and reduce the snapshot overhead. And again, and then the other key is the transparency. So we're capturing the entire process, its memory states and network cache, everything that's needed so that this checkpoint can also be restarted. This checkpointed application can be restarted on another compute instance, another pod, even on another.
Oh, wow.
Yeah, so
you can actually like clone from a snapshot or create a new instance of the entire training job from a snapshot. Is that correct?
At some point you could. Right now we can clone individual nodes. At some point, we'll be able to clone the entire cluster. Yeah, so there's.
Oh, wow. Okay, that's awesome.
Yeah.
So how does all this work with Kubernetes, right? Like you mentioned the checkpoint restore in user space, the Creo project. Like if I'm a Kubernetes platform engineer today, how do I get this or try this out on top of my cluster?
So we've most things the standard automation pattern in Kubernetes is build an operator. So that's exactly what we did. We built a Kubernetes operator that wraps this checkpointing technology with all these enhancements I talked about into a nice convenient operator, which all you have to do is deploy this operator on the controller, and then go into the targeted applications that you want to have checkpointed and annotate in the YAML files. Okay, checkpoint this one, don't checkpoint that one. And so by process ID or application or process tree, we can checkpoint specific applications. And what happens is, like currently, is when you have a node, a pod eviction signal coming from the scheduler saying, hey, we got to boot you out, we got to make room for something else or whatever, we'll automatically trigger the checkpoint. And then when the scheduler tries to relaunch that pod on another node or wherever, we'll automatically trigger the restore process. So we will, in the interim, we'll park the copy of the memory and any ephemeral files into a persistent via PVC on Kubernetes. So that way, there's no more cold restarts. We call it hot restarting of the application. So it's almost as fast as a live migration, but it's actually using a checkpoint.
Gotcha. Yeah. Like so many use cases like show up here, right? So first of all, like let me start. I have a list of questions that just came up because of what you just said. Okay. You said we have to. You can annotate resources. So are you annotating the custom resource that your operator is deploying and asking it to like take 5 of the namespaces that exist on my cluster and take make sure that you are checkpointing it at regular intervals, or you're going into those Jupyter notebooks or resources that, let's say, you're running TensorFlow on Kubernetes, you're going inside that pod specification and specifying or annotating it in a certain way to say that, okay, this has to be checkpointed right now or before it gets evicted.
It's funny you mentioned Jupyter notebooks, because that actually is one of the use cases that I think we're working on, and actually other people like Azure Cloud, I think, have already implemented. And so the idea there is that this checkpointing is not only useful just for compaction of driving up GPU utilization, but a lot of times a data scientist is working on his Jupyter notebook. He decides, going to go home for the evening, and he doesn't even shut his system down. He leaves it in some unknown state. Yeah. And so what happens is that you can automate this to the point where you say, well, this notebook's been idle for no activity for the last 20 minutes. We automatically can give it an eviction signal, do the checkpoint, save his notebook, and then when it comes back,
those resources.
It comes back up, and we can save power, shut down the whole instance, and things like that. So it can be used, definitely used in that kind of use case. And like I said, by implementing it, leveraging namespaces and things like that, you can checkpoint whole areas, whole groups of applications, or specific ones, and things like that. Yeah.
Gotcha. So how do you monitor if a notebook is idle for some time? Like that's something is happening inside the thing, right? Like from a Kubernetes perspective, you wouldn't know if are you monitoring the CPU and memory utilization for a specific pod, or how do you know if a notebook is inactive for a while?
That's one way to do it. I think there's ways through the Jupyter. If you're using something like Jupyter Hub, which is a hub for these things, I think there's ways to detect whether something is changed at all or not, and then use that to trigger a shutdown. Now that actually is interesting because for some applications, not necessarily for AI ML applications, we do monitor CPU and memory utilization. So we have a technology we call wave writing, where we look at we heuristically kind of learn the behavior of a particular application memory and CPU consumption, and so we can automatically, even forget trying to use us on spot instances or something. We can automatically decide, hey, this compute instance is not large enough anymore. We're starting to see memory spilling to disk, and so we better automatically migrate it or to a larger instance. So we can do things like that, and the reverse. We find out there's too much memory, we can downsize it. Same with the number of cores. So we look at CPU utilization and memory spillage and utilization, and so we can literally wave ride the size of the application as it maybe changes, fluctuates. And so between that and also checkpointing and allowing people to use spot instances on the cloud, because now we don't care if the thing gets killed, whether the Kubernetes scheduler kills it or the
cloud provider takes,
the cloud provider decides to shoot it because there's a spot instance. Doesn't matter. We'll checkpoint it and be able to restore it, keep the job running. So,
that's an awesome use case, right? Because I was listening to like a reInvent talk that Anthropic did last year, and they heavily use EKS, and they were using the Carpenter project, which automatically spins up new worker nodes that are GPU based to run those training jobs as they need more GPU capacity. But they didn't talk about what happens when they are not fully utilizing that node. Like, okay, if the pod goes away, even if it was using 30%, at that point, they'll remove the node from the circulation and they'll stop paying for it. But if it's over provisioned, then there's no way to actually identify that. So I think this is like a very specific use case that will be super helpful to people that are in this ecosystem and trying to train this model. So you said it's Wave Rider, right? We'll make sure we find that and add.
We have two buzzwords. One is called Spot Surfer, which is designed to surf different spot instances. So we have long-running EDA workloads that might take 2 weeks to run, and it may go over a dozen different spot instances over that time. But we'll run it to completion without having to have any cold restarts.
Oh, wow.
And even the Wave Rider allows us to upsize and downsize the workload. Some applications are fairly deterministic. Others have huge fluctuations in memory, CPU utilization. So we've seen up to 75% compute cost reduction by using a combination of Spot Surfer and Wave Rider in our product. And we're taking those technologies and we're going to be bringing those in the near future with this new Kubernetes snapshot operator into building a scheduler for GPU clusters for AI ML. Yeah, that's
wow. And again, there are like organizations that are trying to get into the AI ecosystem or trying to use these AI technologies. Definitely have a budget set aside for it. But since we are on this podcast, I want to ask, like, everything that we spoke about, right? Is it open source or is it like a paid offering from Memverge? Like, where do we draw the line?
Yeah, the core project that we built a lot of our stuff on is called Creo, checkpoint restore for in user space.
Yeah.
And we have been contributing to that. We've been actually partnered with NVIDIA to develop GPU snapshotting with Creo. And all that's going to be contributed to the project. But we've taken that core and we've wrapped a whole user interface, a platform, or transformed it into a Kubernetes operator. So we're building. So we're both contributing and building something on top of that will be a subscription, typically a subscription-based kind of thing that customers can deploy and use it to, drive up efficiency and.
So if you're saving somebody 75% of their GPU spend, like, that's an easy line item on their budget. Like, for sure. And you said you were working with NVIDIA already. So is all of this specific to NVIDIA or doesn't matter? You can use Intel-based GPUs, AMD-based GPUs, any GPUs basically that the user wants to use?
Right. So the Creo project, the core part of it is, it's open source, and there is a pluggable device driver architecture to it. So besides NVIDIA, AMD actually on the, I think it's the MI300X, or I think it is what it's called, their GPUs has actually also has got a pluggable driver for Creo. So we can support that also. And then, we're waiting for Intel to come along. So I'm pretty sure all of them are going to implement this, because it's going to be a checkbox requirement for running any kind of AI ML model at scale. We're going to need to be able to move workloads around and pack things efficiently. It's just, if nothing else, for saving the planet, the amount of electricity that's going to be used to run all these AI inferencing systems. Yeah.
Gotcha. And do you have customers that you're already working with, or users, right, from the ecosystem that you're already working with? Can you share some examples?
Yeah, so we ourselves have a lot of examples in the computational biology area. That was kind of our starting point for this wave riding and spot surfing. So if you go to our website, you'll see a lot of either academic or industry partners on that side, like the TGen or Columbia University, things like that.
Gotcha.
Are using us to just to cut compute costs very simply, and then also on the EDA side, the chip design area, we're starting to see a lot of traction there. Just spoke at the Cadence Live event, and there's a lot of interest in deploying us. We have some sites already deploying us because those EDA workloads are also very long running batch problems. So what's interesting is that the whole industry is, including the AI area, AI ML is basically another long running batch, or a continuous service, like what inference is going to be. So this kind of as soon as I think as soon as we get out of the experimentation phase overall in the industry, and people start seriously looking at putting this into production deployment, that's when you're going to see our this kind of transparent checkpointing talked about more and more. Actually, one of the leaders in this area, I would say, one of the hyperscalers is Azure. They are using this checkpointing to do exactly what I was describing earlier, to improve the resilience. Like I said, these GPUs, once you go up to scale, they're burning out like light bulbs, and you need to be automatically, cut in and out of production. And then also they're shutting down idle notebooks, automatically, and without losing the guy's data. That's another use case. So resilience.
So these are great use cases, right? For sure. Yeah. Something that, since you were bringing up batch so many times, something that came to my mind. I was at Supercomputing Conference last year in Denver, and there were a lot of HPC guys. And for them, right, I think batch is more important than the orchestration capabilities that Kubernetes provides. How, do you offer some solution where people can use the Wave Rider or the Surfer capabilities and batch their workload so that they can, as you said, bin pack more things more efficiently, or right size the size of the cluster with the number of nodes that they have?
Oh yeah, absolutely. So we're working. We also regularly go to the supercomputing conferences. We've been working with Slurm, with LSF. Those are the major schedulers, resource managers for that community. And then also on the Kubernetes side, there's actually multiple batch efforts going on, because again, AI ML is a batch operation. Yeah. So there's a project called Q we're working with, things like that. So yeah, absolutely. On the batch side, matter of fact, prioritizing jobs. This job has higher priority. We'll checkpoint the other one, and then and launch this one, and then restore the other one when the high priority job has gone through. Things like that. So yeah, there's a lot of applications, definitely in the HPC side. Yeah.
Perfect. I knew about the Q project, but I didn't know that you guys were a contributor. Man, that could have been a whole another set of questions for you today.
We're not a contributor yet, but we're starting to get involved in that, because I think that's actually there's that project. I'm trying to remember, there's a couple of other projects slipping in my mind. To be honest with you, I went to KubeCon and last in Paris, and I walked away, and it sounded like there were about at least 6 batch projects going on. It's like, we work with. Yeah. But I think
two years back, it was all around Kubernetes security, like 6 different open source projects, if not more, enabling users or developers to shift left and things like that. So Kubernetes KubeCon always has a theme where you'll see most of the vendors talking about the same topic.
Yep.
Gotcha.
Cool.
Okay, so I know we are coming close to the time that we have allotted for this episode. This has definitely been super helpful, not just for me. In just the 2 conversations that I've had with you, Bernie, I've learned a lot. I'm sure our listeners have learned a lot too. But if they wanted to follow up, learn more about it, maybe get some hands-on, try it out in their own environments, where do you recommend they go and what resources should they check out?
Yeah, so for example, we'll start with our website, www.memverge.com, and then from there you can, if you want to test drive this WaveWriter or Spot Surfer software, we have some free trials for that. There's also use cases on the website, and then also we have demos for GPU Snapshot. That hasn't been production released yet. But we definitely have the demos, so we can demo the GPU snapshotting for things like TensorFlow or whatever. And then also, if somebody has even more detailed questions, you can find me on LinkedIn, or you can reach out to me at bernie.wu@memverge.com and send your questions in.
Awesome. Thank you so much, Bernie, for your time today. Like, this has been an awesome learning experience for all of us. I'm sure we'll talk in the future. Like, you have an open invitation. Like 6 months down the line, a year down the line, if you have something really cool to talk about, just hit us up and we'd love to have you back on.
Okay. We look forward to that. Great. Thank you.
Okay, that was a great episode, or a great interview with somebody who's doing this on a day in, day out basis, and not somebody like me who's more focused on the Kubernetes storage ecosystem, right? So this has been an awesome interview for me. I think the things that stood out were definitely the evolution from stateless to stateful. I know with every new piece of technology, right, we see an increased rate with which users are adopting things, and increased rate with which changes happen. So like Kubernetes introduced in 2014, I know we have like a 10-year celebration in a couple of weeks that Google is hosting in their Mountain View offices. But when Kubernetes started in 2014, it was meant for stateless, and then 2017 timeframe is when they started talking about data on Kubernetes, and we have come a long way from there. With AI on top of Kubernetes, when it started again as a stateless thing, and now in less than 2 years, we are at a point where people are talking about how we can make things stateful. So data is always important, right? Data is the new oil, or data is the new plutonium, or whatever metaphor you want to use for data. But data is super important for organizations. So I'm glad that we are seeing this transition. But then talking more specifically about model checkpointing, I like how the developers, right? Like, I know we always talk about shifting left and giving more capabilities to the developers so they're not blocked, but then at some point they get overwhelmed. So I like this balance. Like, it's not up to the data scientists to always be responsible for checkpoints and making sure that they are saving all of their data. The ops team need to share some of these responsibilities as well, and tools like Memverge can definitely help do that. I really like the discussion around how they have these WaveWriter and Spot Surfer extensions or offerings, where they will monitor if your Jupyter notebook has been idle for 3 hours, and you can basically take those GPU resources back, scale down your cluster. Or Spot Surfer, like basically look for instances that are available and right size your Kubernetes cluster. All of those sound like really cool solutions. Personally, I would I'm going to check it out and get my hands dirty. I know GPU resources cost a lot of money, so might take me some time, but this, if you are in this ecosystem and if you are evaluating or already running some training jobs, this is definitely a solution for you to check out. I know this is not like a vendor specific podcast. I was just happy with the discussion and the technologies that we discussed today. With that, that brings us to the end of today's episode, right? One thing that Ryan and I always like to ask to our listeners: please give us a rating on the podcast app where you listen to the podcast. Give us 5-star reviews. 4-star works too, but hopefully 5 stars if you find value here. If you are an audio listener, which is majority of our listeners, go to the YouTube channel, just hit subscribe, give our videos a like, and share it with others. That really helps us work the algorithms and helps us expand our listener base. We if I'm being candid, like, we are at a good number. We are happy with it, but it's always good to keep growing. So help us grow, and we'll keep bringing in more and more interesting guests on the podcast. With that, this brings us to the end of today's episode. I'm Bhavin, and thank you for joining another episode of Kubernetes Bytes.
Thank you for listening to the Kubernetes Bytes podcast.